Welcome to Sri Learning Academy. Let's simplify critical section problem. Imagine two people trying to edit the same document at the exact same time. One changes a sentence, the other deletes a paragraph, and suddenly the final file becomes messy or incorrect. This same kind of problem happens inside an operating system when multiple processes or threads try to access shared data together. They may all be running correctly on their own, but the moment they touch a common resource without coordination, problems begin. This is where one of the most important ideas in synchronization comes into the picture: the critical section problem. It is not just a theory topic, it affects real systems like banking software, ticket booking platforms, printers, databases, and even mobile apps. Understanding this concept helps us see how operating systems maintain order when many tasks run at once. To understand it simply, imagine a shared resource, such as a variable, a file, a memory block, or a printer. If many processes need to use that resource, there must be a safe way to access it. The part of a program where shared data is accessed or modified is called the critical section. This section is critical because if two or more processes enter it at the same time, the shared data may become inconsistent. For example, suppose a social media post has 100 likes and two users hit the like button at the same time. One process reads the count as 100 and adds 1. Another process also reads the same 100 and adds 1. If both write back without coordination, the final count may become 101 instead of the correct 102. The issue is not counting. The issue is concurrent access. Now think of a railway ticket counter with only one booking clerk. Many passengers may be waiting, but only one person can stand at the window and book at a time. If everyone pushed forward together, bookings would be wrong, payments would clash, and confusion would follow. The operating system treats shared resources in a similar way. It must ensure that when one process is using the critical section, others wait outside. Once the first process finishes, another one may enter. This controlled entry prevents race conditions, which we discussed earlier as situations where final results depend on unpredictable timing. The critical section problem is essentially the challenge of designing a rule system for safe entry and exit. A process that uses shared data is usually viewed in four logical parts. First comes the entry section, where the process requests permission to enter the critical section. Then comes the critical section itself, where shared data is accessed. After that comes the exit section, where the process signals that it is done and releases access. Finally comes the remainder section, where it performs all other normal work unrelated to shared resources. This model is useful because synchronization solutions focus mainly on the entry and exit sections. If those two are handled properly, the critical section remains safe. You can imagine entering a library reading room. You check in at the door, sit inside quietly, then check out when leaving, and continue your day elsewhere. Now, the big question becomes this: what should a good solution guarantee? The first requirement is mutual exclusion. This means only one process can be inside the critical section at a time. If process A is updating shared data, process B must wait. This is the most basic rule. Without mutual exclusion, there is no protection at all. Think of a washroom with one lockable door. If one person is inside, another must wait outside. The lock is enforcing mutual exclusion. In operating systems, locks, semaphores, and other mechanisms later achieve this behavior. But at this stage, we focus on the requirement itself. The second requirement is progress. This means if no process is inside the critical section and some processes want to enter, the decision of who enters next should not be postponed forever. In simple words, the system should keep moving. It should not freeze while processes wait unnecessarily. Imagine an empty toll booth with cars waiting, but the gate never opens because the controller cannot decide who should go first. That would be wasteful and irrational. Similarly, in an operating system, if the resource is free, some waiting process should be allowed in within a reasonable time. Idle resources should not remain unused while requests are pending. The third requirement is bounded waiting. This means once a process requests entry into the critical section, there should be a limit on how many times other processes can enter before it gets its turn. This prevents starvation. Without bounded waiting, one unlucky process might wait forever while others repeatedly jump ahead. Picture standing in a queue where new people keep cutting in front of you. Technically, the line is moving, but you never reach the counter. That is unfair and dangerous in computing systems too. Important tasks may be delayed indefinitely unless waiting is bounded. Let us combine these three requirements with a practical example. Suppose three processes want to print documents using one shared printer. Mutual exclusion says only one process can send data to the printer at a time. Progress says if the printer is free and jobs are waiting, one of them should start soon. Bounded waiting says a job that has been waiting should not be ignored forever while newer jobs keep printing first. If all three conditions are met, the printer system behaves efficiently and fairly. If even one condition fails, users experience errors, delays, or unfairness. So, how are these problems solved in practice? At a basic level, solutions use some shared control mechanism to coordinate entry. A process checks whether the resource is available. If yes, it enters. If not, it waits. When finished, it releases the resource. Early software solutions use flags and turn variables. Later, hardware instructions like test and set and compare and swap improved reliability. Modern systems use mutexes, semaphores, monitors, and condition variables, which we will study in upcoming topics. Each of these tools exists because the critical section problem needed practical answers. One more subtle point is that solving the critical section problem is harder in concurrent systems because processes run at unpredictable speeds. One may pause, another may be preempted by the scheduler, and another may suddenly resume. That means solutions cannot depend on timing assumptions like process A will finish in 2 seconds. Good solutions must work regardless of CPU speed, number of processors, or execution order. This is why synchronization is such a deep operating system topic. It is not about speed alone. It is about correctness under uncertainty. In the end, the critical section problem teaches a powerful lesson. Sharing resources is easy, but sharing them safely is hard. Whenever multiple processes access common data, coordination becomes essential. Mutual exclusion keeps data safe, progress keeps the system active, and bounded waiting keeps it fair. These three principles form the foundation of synchronization techniques used throughout modern operating systems. Once you understand this topic, later concepts like Peterson's algorithm, semaphores, mutexes, producer, consumer, and readers, writers become much easier to grasp because they are all different ways of answering the same question: how do many processes share one system without creating chaos? That is it for this video. See you in the next one.